In this lecture, we consider one of the most important statistical tools in multivariate methods, that is, principal component analysis. Why this technique is important? To apply some statistical methods we need uncorrelated variables. One example is regression analysis. If the variables are correlated, how do we obtain uncorrelated variables? Also, for a particular practical situation, if many variables are available, and if we prefer to use a smaller set of variables, then how do we select these variables? Principal component analysis provides answers for both these questions. Using principal component analysis, we can transform a correlated set of variables to an uncorrelated set of variables, and we can reduce the dimensionality of the data, that is, to obtain a smaller set of uncorrelated variables. To understand the concepts in principal component analysis, we now consider an example having two variables. In this example we have two variables x1 and x2. Note that the mean of the original x1 variable is 8 and its variance is 23.091. Also, the mean of the original x2 variable is 3 and its variance is 21.091. Then, we consider the mean corrected variables. The mean and variance of the mean corrected x1 variable is 0 and its variance is 23.091. The mean and variance of the mean corrected x2 variable is also 0 and its variance is 21.091. What do you notice here? For both variables we have the same variance for original and mean corrected data. When analyzing data we consider the variance of the relevant situation. Since the variance is the same for the original data and the mean corrected data, we can use mean corrected data for the analysis. Now, we use mean corrected data to find the cross product matrix SSCP as shown here, and the covariance matrix S using this expression. Note that the covariance of the two variables x1 and x2 is 16.455. The total variance of the system is 44.182. Now, we can find the percentage of total variance accounted for by each variable by using the variance of each variable and the total variance. For the variable x1, it is 52.26%, and for x2 it is 47.74%. Using covariance matrix, now, we can find the correlation matrix R. The correlation coefficient between the two variables is 0.746, and it is a high positive correlation. Now, we try to make the variables uncorrelated by rotating the axis. First, we rotate x1 axis to make an angle theta degrees with x1, and name the new axis as x1 star. To find the coordinates of the observations with respect to x1 star, we can use this formula. The values of x1 star is given here, when the angle theta is 10 degrees. Then we find the mean and variance of x1 star values. Since the mean is 0, still these values are mean corrected. Now, compare the variance of x1 star with the variance of x1, which is 23.091. After rotating the x1 axis we obtain the new variable x1 star, and its variance is higher than x1. Therefore, the percentage of total variance accounted for by x1 star is also higher, and it is now 64.87%. By considering different angles we calculate the variance of x1 star and the respective percentages. We can note that when theta increases the variance of x1 star and the respective percentage increases up to a certain level and then decreases. When theta equals 43.261 degrees we have the maximum variance and percentage. Using the percentage values and the respective angles, now we obtain this plot. This plot also shows that when theta increases the respective percentage of x1 star increases up to a certain level and then decreases. When theta equals 43.261 degrees we have the maximum percentage. Now, we fix theta to 43.261 degrees, and rotate x2 axis perpendicular to x1 star axis to obtain the variance that is not accounted for by x1 star. Name this new axis as x2 star, and the values of x2 star can be obtained by using this expression. In this table we can see the x1 star values, x2 star values, their means, sum of squares and variances. Using these values we can easily find the cross-product matrix SSCP, variance-covariance matrix and the correlation matrix. Refer the diagonal values of the variance-covariance matrix and correlation matrix. They are 0. Therefore, the two new variables x1 star and x2 star are now uncorrelated. The variances of x1 star and x2 star are 38.57 and 5.606, respectively, and the total variance does not change with compared to the original coordinate system. In this plot, the dotted lines show the new axes x1 star and x2 star. If we plot observations with respect to the old or the new axes, we can note that the positions of the observations do not change. This means, the total variance of the system remains constant. The new axes or variables are called principal components, and the values of the new variables are called principal component scores. The percentage of the total variance accounted for by x1 star is 87.31%, and the percentage of the total variance accounted for by x2 star is 12.69%. The two new variables x1 star and x2 star are now uncorrelated. Since x1 star contains 87.31% of the total variance, instead of the two original variables x1 and x2, only the variable x1 star can be used to represent the data. Then, the loss of information is only 12.69% of the total variance. Instead of rotating axes to obtain principal components, do we have any other simple method? We try to find an answer for this question after finding eigenvalues and the corresponding eigenvectors of the variance-covariance matrix of the data set. Look at the eigenvalues. They are exactly equal to the variance of x1 star and x2 star. We can use the eigenvectors to obtain principal components as shown here. Now, we try to understand the theoretical background behind this eigenanalysis. Generally, the principal components are linear combinations of the p-random variables x1, x2, up to xp. Then, using p number of x variables, now we write p number of linear combinations, y1, y2, up to yp. These linear combinations represent the selection of a new coordinate system, and the new axes represent the directions with maximum variability. Note that, the variance of yi is equal to li-sigma li, and the covariance of yi and yk is equal to li-sigma lk. If y1, y2, up to yp represent the principal components, then they should be uncorrelated, and their variances should be as large as possible. Therefore, the first principal component y1 is the linear combination having the maximum variance L1-sigma L1. But, we can increase the variance of y1 by multiplying L1 by any constant. Therefore, to avoid this discrepancy, we consider only the coefficient vectors of unit length, that is L1-L1 equals to 1. Now, the first principal component is the linear combination y1 which is L1-x, that maximizes the variance of y1 subject to L1-L1 equals to 1. The second principal component is the linear combination y2 which is L2-x that maximizes the variance y2 subject to L2-L2 equals to 1, and the covariance between y1 and y2 is 0. Note that, when this covariance is 0 the two principal components y1 and y2 are uncorrelated. Similarly, ith principal component is the linear combination yi that is li-x, which maximizes the variance yi subject to li equals to 1, and the covariance between yi and yk is 0 for all k less than I. This means, the ith principal component is uncorrelated with all other previously defined principal components. In place of li, if we use eigenvectors, we can obtain principal component which satisfy the above conditions. Suppose the variance-covariance matrix of vector x is sigma with eigenvalues lambda 1, lambda 2, up to lambda p, and eigenvectors e1, e2, up to ep. Since the matrix sigma is positive definite, all eigenvalues are positive. Now, we can write the ith principal component yi as ei-x, and its variance is ei-sigma ei, which is equal to lambda I. The covariance between yi and yk is ei-sigma ek, which is equal to 0. To obtain the total population variance of the system, we can either use the sum of the variances of all x variables or sum of the eigenvalues. To find the proportion of total variance due to each principal component, we can use their variances and the total population variance. For example, the proportion of total variance due to the principal component yk is lambda k divided by sum of lambda I. After finding these proportions, if 1, 2 or 3 principal components together represent a high percentage, then we can use them to replace the original p variables without much loss of information. Since EKI is proportional to the correlation between yi and yk, we can use it to find the importance of the xk variable to the ith principal component. To find the correlation between the principal component yi and the variable xk, we can use this formula. In this example, the variance-covariance matrix sigma of a data set is shown here. Using sigma, we now find principal components, their variances, proportion due to each principal component, and the correlation coefficients between each principal component with each variable. Based on these correlations, we can construct the loading matrix. Note that both variables x1 and x2 are uncorrelated with x3, since the respective covariances are 0. Eigenvalues and eigenvectors of the variance-covariance matrix sigma are shown here. Then, using the eigenvectors, we can write the 3 principal components y1, y2, and y3. Note that the variable x3 is one of the principal components, since it is uncorrelated with x1 and x2 variables. The total population variance in this case is 8. Since eigenvalues represent the variance of the respective principal component, now we can find the proportion of total variance due to each principal component. The proportion of total variance due to y1 is 73%, the proportion of total variance due to y2 is 25%, and the proportion of total variance due to y3 is 2.125%. Therefore, without much loss of information, we can drop y3. Then, the first 2 principal components account for 98% of the total population variance. Hence, with little loss of information, we can replace the original 3 x variables with the first 2 principal components. Now, we find the correlation between the principal components and the original variables. The correlation between the first principal component y1, with 3 x variables can be derived as shown here. Note that the first principal component y1 has a high positive correlation with x1, and high negative correlation with x2. But, the first principal component y1 is uncorrelated with x3. Similarly, we can find the other correlation coefficients, and then we can construct the loading matrix as shown here. We already noted that the first principal component y1 is highly correlated with both x1 and x2. But, there is no correlation with the second principal component y2 with both x1 and x2. However, the second principal component y2 is perfectly correlated with x3. Also, the correlation between the third principal component y3 with x variables are negligible. The importance of constructing loading matrices is that we can identify